Okay, in this video we'll be addressing the other type of problem in this topic, which is all to do with flow. Now, it's a rather vague word. It could be the flow of physically water going through pipes, or sometimes we use this to model traffic situations or people going through areas or data transfer or other things that we won't really have to look at in this course. But to start with, I want you to think of such a network as actually modeling water flowing through pipes. Okay, so the numbers on the edge, the weights of the edges will represent, for example, how much water can flow through per minute. Okay, so you can probably imagine that this pipe over here, the 6 pipe, would be somewhat thicker, I guess, than these two there, because it can allow for more water to flow through every minute. The starting point is something we call the source, and the end is something we call the sink. Okay, and the main question we'll be trying to answer in this section is, what is the maximum flow through the whole network? How much water can we pump through this whole system from source to sink? Okay, because this pipe can hold 6 liters, say, per minute, and it can split across the 4 and the 4. Maybe it goes 3 in there and 3 in there, or it could be 4 in there, 2 in there. Really, we don't care. Okay, we are only really interested in what is the maximum amount that can flow from the source to the sink, however it gets there. And in this case, it would be the 6. Okay, and something to sort of keep in mind for this one would be, it doesn't really matter how fat these pipes here are now, because this can only hold 6 liters, then improving these 2 pipes won't really change this maximum flow. Okay, so hold that thought. If we change a 6 to a 10, right, how much can we flow through now? Well, you might try and pump in 10 liters of water through here, but only 8 can make it out here in total. So that's why you can't actually send 10 liters through this pipe here, because 2 of those liters will have nowhere to go. It can only go maximum 4 in here, 4 in there. Okay, so the maximum flow in this network would just be 8, and that's just because of this guy. Okay, and this time, doesn't matter how fat you make this pipe here, it's not going to change the fact that this is now your bottleneck. This is now what is limiting the flow across the whole network. Okay, one more quick example of that. Say we make it so that there's 2 pipes going from the source to this middle vertex now, with a capacity of 2 and capacity of 5. Right, so what's the max flow now? Well, these 2 together can hold 7, while these 2 together can hold 8. Okay, so your sort of bottleneck this time would be because of these 2 pipes being only able to hold 7 liters of water. Okay, and that's the main idea we'll be using, trying to locate that tightest bottleneck that's going to limit how much you can flow through the whole system. And to locate this bottleneck, we do something called a cut. We do something like this, right? A cut is a line like that that separates the source and the sink. So you must have the source on one side of the cut and the sink on the other side of the cut. Okay, and what we say the capacity of the cut is it counts the sum of all capacities of edges going through this cut from the source to the sink. Now, it looks complicated, but it's not really. Again, we're just trying to find that tightest bottleneck. So if we cut our network down here, we say, what's the sort of bottleneck I'm seeing there? I'm seeing that it can only let through 2 liters through there, and 5 liters through there. So the size of my bottleneck must be 7 liters in total. Okay, so that's the size of this cut. Whereas if I cut it, say, over here instead, well, I've got 4 liters going through this cut and another 4 liters going through. So how much water will this cut let through? In total, it will be 8 liters. That's why in this network, my maximum flow is the 7. Because that's my tightest bottleneck. This is what's going to limit the flow across the entire system. Okay, so I can almost forget about this 8 one here. That's going to be the maximum flow across the network. Okay, now notice I also say it's only the edges going from the source to the sink. That's pretty important. And we can illustrate this sort of maybe obvious fact that it's not going to help if I put a pipe going this way, right? Because I'm trying to get from the source to the sink. So even if I install another pipe that's going to the left here, that's not helping me achieve my goal. Okay, so that's not going to count to this cut capacity here. Okay, I hope it's sort of obvious here. It's just that when the network gets more complicated, sometimes you really need to be deliberate in keeping track of whether your edges are going through your cut from the source to the sink, or whether they're going backwards, and so not really being helpful at all. Okay, but the thing we've actually already talked about is actually the fact that the maximum flow across the network always equals the minimum cut. Okay, the maximum amount of water I can pump through the system is exactly the size of that smallest bottleneck. And I hope the examples we've already shown you are enough to convince you of that. It is quite difficult to fully prove, and we're not going to do that in this course. But it is true, and you can and should use that this maximum flow is exactly the size of the smallest cut you can find across your network. And what that means is for the remainder of our sort of work here, we'll be aiming to find this minimum cut. So it's kind of weird. Even though we want to find the maximum amount of water we can put through, we're going to do that by actually finding a minimum cut for our network. Okay, so let's see some examples of that. Let's take this guy here. Okay, now we know that a cut that separates the source from the sink has to somehow hit one of these top edges here. Okay, so we're going to have to use a bit of guess and check, almost trial and error, a bit like finding the shortest path last year. But we can sort of direct this trial and error, we can sort of direct our attention. So if we look only at this top path here, right, I think the edge that is most promising for minimizing the size of our cut would be the 4. And the only reason you wouldn't take the 4 is if it forces you to maybe cross through another edge, which is kind of big, okay? Because again, we're aiming for the minimum cut. Okay, but we can try. If we go through the 4 here, we can cut it this way, or that way, or that way. So which one would we take? Well, I guess we were looking for the minimum cut, so we'd take the one going through the 9 there, okay? Now, you might be a little bit worried about the 5 here at first, but you shouldn't be. Why? Because if you look at the way we've cut our network, A actually belongs on the sink side, while B belongs on the source side. So a pipe going from A to B is actually going backwards and does not count towards our cut. So actually, this cut only holds 2 edges. It's the 4 and the 9. The 5 doesn't do anything. And so we find our minimum cut of 13. Okay? Now you can check your other options and you'll see that none of them get smaller than this. So that's a 16 there. That's a 14. There's another 16. And then everything else is just going to be bigger. Okay? But our minimum cut is 13. What that tells us is that the maximum flow through this network is also going to be 13. Okay, and just for this one, we'll even show you how that flow might work. So if we look at maybe just the bottom route from the source to the sink, how much water can we pump through here? Well, it looks like the maximum amount is we can put 9 through all of those ones. Any more than 9, and this pipe here will burst. Okay, so we can only put 9 through there. What about the top route, this one here? Well, I think we're limited this time by this edge, and so we can only pump 4 through there. And that's all we can do. Okay, you can try and use the 5, but you actually can't because there's no more water that you can put through this pipe here, and so there's no way you can actually use the 5. He becomes a useless pipe. Okay, so that's our maximum flow through this network here. Okay, all right. What about another example? So same sort of thing. I might start by looking at the top set of edges. And again, we're looking for a minimum cut. So we might be thinking, let's start by trying the 3. That looks like a good place to cut because it's the smallest edge out of these guys here. But you see how this time, going through here, once I'm there, I am forced to either cut this way or that way. Okay, there's no other way to get out of this mess here. If I am really to separate the source and the sink, I've got to go through one of these two. Okay, and actually both the 7 in this cut and the 8 in that cut will have to count because it is going from the source side to the sink side for the 7 and for the 8 as well. So what that means is while the 3 looks kind of good, you get yourself into a situation where you're forced to take the 7 or to take the 8, and so actually it doesn't look as good as it first did. Okay, what about the 6? Well, same deal there, unless you go straight down the 8, so the 14 here is an option. Okay, and going through here is also an option, but you're then forced to take the 8 as well. So the 6 looks like it could be good, but the best we can do, the smallest cut we can do, would be the 14 through here. Can we do better than the 14? Well, what if we go with the 7? Looks like we can do a 13 here. So the minimum cut this time would be our 13 going through there. Okay, so I hope you can see it's kind of trial and error, but there's a sort of direction to how we do this trial and error. And it's a bit like shortest path in the sense that sometimes you'll just miss it. With a bit of practice, you can hopefully get a bit more reliable at doing this, but it will take you a few goes to be able to spot those smallest cuts. Okay, so that's our 13 in this case here. One more thing before we move on. What it means for the minimum cut to be here is that these 2 pipes are the ones we expect to be fully maxed out. Okay, so if you go ahead and make these pipes here able to hold more water, well, that's not going to really help. Okay, your bottleneck is still going through here. And so in questions where you need to interpret the story and maybe make some suggestions or some recommendations for how to improve the sort of capacity of this network, you better be focusing on these sorts of edges here, or at least trying to make more routes going through if that is appropriate to your question. Okay, improving things over here isn't going to help because that's your bottleneck. Okay, you'll see more about that when you do your work. Okay, last one here. This is from an exam paper. This is a network. I think it's a traffic story. And a cut was already given to us. And I think the question was asking whether this was a minimum cut, and if not, to find it. Okay, so this cut here, well, first, what's its capacity? Well, BD is 50, BE 75. This guy is going the wrong way, so we don't count him. Okay, we will count AC though, and so that gives us a total of 325. Okay, 50 plus 75 plus 200. But we are interested in whether that's the minimum cut, so can we do better than this? Can we find a smaller cut than this one? Well, first I think this part here is a good start. What tells me that? Well, again, you have to cut through something from the top. 350 is obviously bigger than what we've got already, and 150 is bigger than this, because this is only 125, right? Then this one here is going to take more than 125. This is 300. So I think this is actually a pretty good start when it comes to trying to find a minimum cut. This is a good start. But do we have to go down to 200? I'm not sure about that. Okay, can we do better than that? Yes, we can if we cut through to the right here, because we're going to take our 125, and rather than go down to 200, we can go through here, which only takes 150. Okay, and so that cut is going to have a size of 275. That's the capacity of this cut, and in this case, I'm pretty sure that is the minimum cut, and so that's going to be the maximum flow of traffic through this network here. Okay, it's going to go through these edges. Okay, so that's how you find a minimum cut. The maximum flow through the network always equals this minimum cut. And if you ever have to, say, make a suggestion or build extra roads to improve the traffic flow through this area, say, you better be focusing on this area and the roads that go through this area. Okay? Don't go fixing things over here. It's not going to do anything because that's your bottleneck. Okay, so see how you go. You've got to try this yourself a few times to get the hang of it. But that's all for now. See you later.